Recording. State the principle of the conservation of momentum. Conservation of momentum is that momentum, which has a symbol of P, which you would need to spell out the word momentum, is conserved as long as there are no external forces. Okay? On a side note, this one is a definition that is 2 points, which means that it's probably slightly more involved. That does not feel much more involved than usual, but it is. Also, force times time is representing the change in momentum. Otherwise, momentum is always conserved. If you don't have a force, external force, and you don't have a time that it's done for, you will have no change in momentum. Speaking of no change in momentum, if we look here, we have two different spheres or balls going towards each other. We have their mass, we have their speed initial, we have their mass, we have their speed initial, and then they both leave going to the right. You have two ways to determine, after looking at the picture, the angle. You could either use the vertical aspect of momentum or the horizontal aspect of the momentum. For me, I think I'm going to use the vertical because the vertical part has to be equal due to the fact that whenever they came together, one was going up, one was going down, they left only moving horizontally, which means the vertical component of the momentum, not their speeds, but their momentum, had to cancel. All right? Which means that mv sine theta of one must equal mv sine theta of the other. The reason I wrote mv is because that's momentum, mv, and then sine theta because that would be the angle, okay, for each one, and they do happen to equal the same angle. All right. Interestingly enough, I think I might have chose poorly. What's going to happen here? They're the same angle, right? What's going to happen to the sine thetas? They cancel out. So that just means that the momentum there would equal the momentum there, but we already have the m and the v and the m and the v, so that failed attempt. So far, not off to a good track. But the horizontal momentums we could also use. They combine to make the final momentum. Okay, so the formula that we have there, I'm not doing the full thing. If we did mv plus mv, regular momentum plus regular momentum must equal, they stuck together, m plus mv final. Remember that formula? But we need to make it horizontal plus horizontal equals final horizontal. We get to horizontal by just doing mv cosine theta plus mv cosine theta is equal to m plus m v final. We can plug in all of the appropriate things. The top one has a mass of 3 and a velocity of 4. So that would be 3, 4 cosine theta. And 2.5 times 4.8 plus 2.5 times 4.8 cosine theta is equal to 2.5 plus 3 v final. If we do a little bit of math there, you end up with 12 cosine theta plus 2.5 times 4.8 is 12 cosine theta. So these are both 12 cosine theta. And if you combine 12 plus 12, you get 24 cosine theta would equal 2.5 plus 3, 5 v final. But the v final was 3.7. I don't know why I didn't fill 3.7 in the first time. 3.7. 5.5, good call. Easy fix. I can just put a 5 in front. Divide by 24, and then cos negative 1. So cos negative 1 of 5.5 times 3.7 divided by 24. If I had to guess, this is a 3-point question, and it is. You could get partial credit along the way by just filling in appropriate formulas. If you do that, you end up with 32 degrees. Make sure you're in degree mode. All right, that one started off pretty difficult. 32 degrees, yep. So, by calculations of kinetic energies state and explain whether the collision of the balls is inelastic or perfectly elastic. So, this kind of bothers me because we already actually know that this is going to be inelastic because they stuck together. Okay, so kinetic energy will not be conserved, but we can still do it. We can do 1/2 mv squared plus 1/2 mv squared. The initials, they had two initials. How did that compare to the 1/2 mv final squared, which they were combined, so that would be like m plus m there. So we had 1/2 of, I think it was 3. 3, and the velocity was 4. Plus 1/2 of the mass of 2.5 and velocity 4.8. How does that compare to 1/2 of 2 plus 2.5 plus 3 times their final velocity squared, which was 3.7? And those don't equal, therefore, they are not considered perfectly elastic. If we do the math for that, you would end up with, let's see, it said before, if you do these, it was 53 joules. And then afterwards, this part is 38. Well, we lost some kinetic energy, therefore it is not perfectly elastic, and it would be inelastic. Inelastic due to kinetic energy being lost in collision. Or you could say kinetic energy is less than the 53 to begin with. Questions with that one? All right. 7 minutes. We're